That's right, yeah. Just for everyone who doesn't know me, my name's Philip West. I'm the current Sibsey North East chair, and just like to say thank you for everyone for attending the event. And just in terms of a couple of housekeeping rules, I think everyone will be muted throughout the presentation. But if anyone's got any questions, if you want to use the chat function and put your questions in there, and Neil will be happy at the end of the presentation to go through the questions and answer them as best as he can. So I'll pass you over to Neil, and you can press ahead with the presentation. Thank you.
Thank you very much, Philip. Right, so I'll just share my screen. So if Philip, if you could just tell me that that's okay and that you can see that.
Yeah, I see that. Yeah, okay. That's all great. Yeah.
Okay, right. Well, just to echo what Philip's just said, thank you very much for attending. Any questions, I'm more than happy to answer them. To just give you a little bit of background on myself, so you know who's talking to you. I'm an engineer. That's how my career started. Worked in research and development for a long time on flow testing of valves for variable volume systems. Did lots of things in a technical department or in a technical role, and then sort of found myself working for a Danish company specifically on district heating. Learned a lot about district heating then via that Danish company, and then set up with Altecnic, and my role as it stands today is really CPD seminars, funnily enough, but also giving design advice, sizing advice on district heating networks to building services consultants all around the UK, all over, basically. But also, as I mentioned, as I was talking to Philip earlier on, I get asked a lot now. It seems to be getting more and more common to review sites that maybe aren't performing as they should be. So that might be at the request of the building owner, the housing association, local authority. It might be at the request of a consultant who's been brought in to have a look at a project that's not performing as it should be, and so on. As part of my role as well, I'm on various trade bodies, such as, I'll try and remember them all, obviously Sibsey and BSRIA, but also the UK DEA, the ADE, MENA, BESA, all kinds of different trade bodies, specifically to district heating, basically. And if I have probably now almost 20 years experience specifically on district heating across Europe and in the UK. So if there's something I don't cover in this presentation, which is quite likely because it's a big subject, of course, district heating, then please feel free to bang it into the chat, and I'll try and answer as many as I can at the end of it. So yeah, I'll push straight on. So who are Altecnic? Well, we're based up in Stafford, just north of Birmingham. We have three divisions. The specifications division, which is the division that I head up. We have our trade, which is basically dealing through merchants. And then we have our OEM division, which is dealing with the likes of Ideal, Worcester Bosch, Baxi, Crane, even as we supply valves to Crane, strangely enough. Lots of other OEM companies, and it's true to say that if you buy a boiler, combi boiler in the UK, it has our components in it. We supply to all the boiler manufacturers. We're owned by Caleffi. They're based in a small village, really, Fontanetto d'Agogna, which is just north of Milan. Terrible part of the world, big mountains, big lakes, and great red wine. So yeah, what's wrong with that? And they're a really huge company. They have 4 manufacturing sites, all based roughly about 20 kilometers away from each other, and all in the same area of northern Italy. And they have a huge amount of branches throughout the world now, but all the manufacturing is still done in Italy. And we're cradle to grave, so we literally will get pour metal, stamp, cast, whatever it happens to be, and then machine it right the way through to testing, assembly, all that kind of stuff. So that's enough about them. I'm going to try and cover all these points on here, so I may go a little bit quick at stages, but hopefully I'll cover the main points that we need to cover. So why district heating is, I guess, the first question, or why heat networks? Well, it is a proven method to reduce carbon emissions. And these two graphs need to be read side by side. They go hand in hand, and I think it's a really impressive show of why district heating really. This first graph on the left hand side here shows the amount of heat supplied to Swedish district heating systems between 1969 and 2015. So you can see it's ever increasing, so more and more buildings being added to the networks, and so on, more networks being created. So the actual amount of energy that's supplied each year has gone up from 1969 all the way up to where it is, where the graph stops here, which is 2016, I think that is, or 15. And you can see it's pretty much got bigger and bigger year on year. You can also see by the rainbow of colours that the sources of energy that are used in those heat networks have got more diversified as they've grown. Now, when we compare that to the graph on the right hand side of the slide, you can see this is carbon emissions, and those carbon emissions have just steadily dropped and dropped and dropped and dropped, and they're right down now to a really low level, despite the fact that the amount of energy delivered by heat networks has massively increased. So that's really why district heating, it's proven technology. It is energy source agnostic. You can use anything or any combination of things, you know, even waste heat. We've done a few projects in London where we're pulling, or we're starting the process by taking heat from the tube, you know, to maybe lift up to say 25, 35 degrees, something like that, and then using something else to top off, and so on and so forth. It's still true to say that the majority of networks in the UK have gas boilers in them in some shape or form, but the amount of heat pump only networks we're now getting involved in has just really, you know, it's stratospheric increase. Really, it's been incredible, the amount of networks. And I think with the latest launch of CP1 talking about future proofing of networks, I think it's really important, we'll come on to it later on, that even if you know, maybe a network is being designed now or installed now and it has gas boilers in it, we need to think about the future, because to be frank, in it wouldn't even be as much as that. I mean, it could be in as little as 5 years' time. We really need to be looking at converting these over to heat pumps. And the reality then, of course, is that your flow temperature is going to drop. So unless you've thought about that in terms of the end equipment, the terminal units, the HRU that's on the heat network, unless you think about that now, then potentially the cost of modifying that network at a later date to heat pumps is massively increased if you have to replace all the HRUs and then maybe look at pipe work and so on. So we need to think about that on any job that's going in, even if it's a, as I say, 70, even 80 degrees C network. Now we need to think about making sure the equipment is suitable for 55 degrees C at some point in the future. So just going to look at why instantaneous HRUs. Well, there's lots and lots of reasons. I don't want to just sit here and read through the slides, but there is an important, there's a number of important factors really on instantaneous production of hot water, of domestic hot water. And the fundamental point here is that your cold water may be coming in at typically, for sizing, we tend to use 10 degrees, but it could be sort of 15 degrees or what have you. That is the thing that makes these networks work, because that water is cold, or cool, very cool, and you need to increase that up to a hot water temperature, and typically now that would be 50 degrees. So you need a lot of energy, but the fact that you've only got 10 or 15 degrees going in means that you can take an awful lot of energy out of your LTHW that's going into the apartment or the HRU, and that gives you a very large delta T on the network, and it is the large delta T and the low return temperature that is absolutely crucial to getting heat networks efficient. And we see networks returning sub 30 degrees if they're designed, installed and commissioned properly. But then again, if you don't get those three areas correct, we see systems with return temperatures of 68 with a 70 degree flow, literally, you know, a couple of degrees. And in fact, I think my colleague who's on this this presentation today actually is the sort of infamous owner or got involved on a project where that we saw a delta T of just a half a degree, and that is just quite shocking. We really need to be better than that. But coming back to delta T, this is the thing that makes the heat network efficient. So anything you can do to increase that, the better. Anything that decreases your delta T is generally bad and needs to be looked into. Now, when you look at storing domestic hot water, then you run into issues really in terms of ensuring that wide delta T. Once that cylinder's 3/4 up to temperature, for instance, your delta T on the network side is going to be relatively low. You've also got to overheat that water because you're storing it, so you have a Legionella issue. So you need to be above 60 degrees C, yet you don't want it at 60 degrees C at your tap. So you're artificially adding more energy in than you need to treat the bacteria that is as a result of what you're actually doing in the building, and then you add more equipment in to bring that down so you don't scald people. So it's very wasteful from that point of view. When you look at sizing of the central plant and the network, there is quite a misconception that people think, well, okay, if I'm putting a cylinder in and maybe it's got a 12 kilowatt coil in it, then I've got 100 apartments. So if I compare that to an instantaneous HRU that might want, say, 35 kilowatts, then obviously I'm going to need a much bigger energy center, bigger pipe work to provide the energy for instantaneous HRUs. And therefore, I want to go with cylinders because it'll be better. Everything's going to be smaller. But actually, that's almost always not the case, because the diversity that you have to apply to the two scenarios is different. So with an instantaneous unit, if you think about it from the point of view of running a bath, it may only take 5 minutes, 7, 8 minutes maybe to run a bath. So the HRU is on demand for 7 or 8 minutes. With a cylinder system, it will take obviously the same time to fill the bath, but then you've got to reheat the cylinder. So that cylinder is likely to be on demand, if you like, for half an hour or so as it's coming back up to temperature. So when you apply diversity, the diversities are very different between an instantaneous system and a stored system. And there's a calculation here I've just done to give you a rough example. If you look at the instantaneous unit, network, and say 35 kilowatts per apartment, domestic hot water demand, 100 apartments, times by the diversity, and that's taken here directly from DS439, which is the Danish standard, which is now pretty much become the standard in the UK. It's referenced in CP1 and lots of other documents. You get a kilowatt figure of 245 kilowatts. Typical delta T here that I've used with a fairly low primary flow temperature of 37 degrees gives you a 1.57 litres per second flow rate to give you your 245 kilowatts. If we look at the stored calculation and we say roughly a 12 kilowatt coil, 100 apartments, the diversity here is now 0.25 if you use BS 8558, and that gives you 300 kilowatts. So it's bigger than the instantaneous demands that you have up here. And then if you work that out into a flow rate, I've actually erred on the side of being positive about the cylinder here and said, 30 degree delta T gives you a 2.38, but there will be many times when that is, you can't achieve your 30 degree delta T. So you can see again, the flow rate is greater as well. So it's something that needs to be borne in mind. One of the other things that I'm seeing quite a lot of is we have a number of consultants who sort of jump to the conclusion where they go, right, but this is a heat pump network, so I've got primary flow of 55 degrees, so I can't get the outputs I need at that low primary flow temperature. So I need to go stored, because then I can put a coil in there and I can use that to raise it up to a higher temperature, the hot water. So I need to go with cylinders. But actually, if we look at this table that's taken directly from CP1, we've got the kilowatt power demands here and the hot water flow rates. And all I've done is do a couple of calculations here. First one is with an LTHW flow into the HRU at 55 degrees. These are maximum calculations, incidentally, using that particular model, the SAT K32107. It's just one of our HRUs, and you can see it'll give you 44.2 kilowatts of instantaneous hot water with that 55 flow on the LTHW side, and you can see that that covers the majority. In fact, it covers all of them. No, it doesn't. That one there, the 3-bathroom, is the only one where we're slightly down on what CP1 recommends is the demand. If we lower that flow temperature even further, down to 51 degrees here, we can see we'll get to 30 kilowatts. You're still covering a number of the apartments here at a very low primary flow temperature. Incidentally, you can see where I've used the domestic hot water, most common temperature that we have now, and we'll talk about this a little bit later, of 50 degrees C. We need to have a difference because this is what's called approach temperatures, which we'll look at a little bit later on. So we've increased that just by 1 degree to give you that approach temperature across here. Personally, and having worked a lot in Scandinavian countries, I would actually be looking at running that at 50 and dropping this down to maybe 46, 47, something like that. So you've got that approach difference, because really 50 degrees C, we as I say, have standardized typically on that in the UK, but it is high compared to what we tend to see in a lot of Scandinavian countries. I'm not going to labour the next slide a lot, but I just wanted to say that if you do need additional power applied into the primary system, into the HRU to give you the output that you need in terms of domestic hot water, there is a much better way of doing it than doing it on the secondary. And we just have this additional cylinder that sits on the district heating, so the heat network flow into the HRU. It's controlled by the HRU itself, and basically what happens is under normal sort of heating or standby, it's not energized at all, this coil, and the HRU controls it, and the moment there's a hot water demand in the apartment, then the HRU itself energizes the coil and just lifts that primary flow going in by an amount, and we'll go up to sort of 10 degrees as a maximum, just to give you a little bit extra heat into the primary side to allow you to produce domestic hot water. The benefits here, of course, is it's on the feed to the HRU, so the diversity that's applied to the additional electrical load is the same pretty much as you would get in DS439. So it's a very high diversity factor that's applied to that additional electrical load. And also, of course, being on the feed into the HRU, it does not do any damage to your delta T across the flow and return. It actually will increase it, of course. So there's major advantages to having any electrical additional energy on the, if I call it the primary, some people call it the secondary. I'm not going to split hairs over that, but if I call it the primary for now, then it's much better to put the element there rather than put it on the secondary, i.e. the domestic feed out from the HRU, because the moment you do that, you hinder the delta T onto the primary side, and you have a much lower diversity factor, etc., and all those things cascade on. So the design process, where do we start and where do we finish? Well, the first thing actually is to look at the flow temperatures, and the only reason these are really the first sort of port of call here is because they will depend on what energy sources you have in your energy center. If you're running CHP, you might be running at 80 or 90 degrees. Similar thing, temperature if it's biomass. If it's if you've got boilers in there, you might be running maybe a little bit lower. It's maybe 70. But if it's a heat pump network, you're probably running at 55. So once you know what your energy sources are, that will dictate what your network flow temperatures are. Then you go straight away from the plant room. We're not interested in the plant room at this point. We need to move right to the extremities of the network and start the calculations in the apartment. So you would look at, are we using underfloor heaters or underfloor heating or radiators? A little bit more on that later on. What kind of approach temperatures are we going to look at? That's the difference between flow temperature in to flow temperature out. What are the realistic hot water outputs that we need and the realistic hot water temperatures? And the only reason I've used realistic there is we have seen over the years a tendency to overestimate the hot water demand and overestimate the temperature, or have a higher domestic hot water temperature than you actually need. And you can see that if you do overestimate these figures here, because this is the point of starting the calculation on the network, then everything else is going to cascade down from that, and everything else is going to be oversized if you overestimate these outputs and temperatures here. So these have to be as accurate as they can be. At that point, once you've got these factors dialed in, you then need to select a HRU to meet the demand, because you now know what the flow temperature is going into the HRU, you know what you need coming out, so you can now do a calculation to work out which HRU you need that's going to give you those, or meet the requirements of your network. By selecting that HRU, you can then work out what the delta T calculations are. And just to be clear, there's a reason why that is after the HRU selection, because manufacturers obviously all look to try and keep the cost down as much as possible. And with a HRU, and specifically a plate heat exchanger, the length of the plate will give you a greater delta T. In general, the depth of the plate gives you kilowatts, the length of the plate gives you your delta T. But obviously a shorter plate is cheaper than a longer plate. So if you have a rather unscrupulous HRU manufacturer, they may go, well, I'm just going to put a short plate in and I can sell it, I can make it cheaper. But actually, well, that's going to harm your network, because it's going to give you a smaller delta T than a HRU that has a long plate in. There are also other factors that within the HRU that affect the delta T calculations. So it's important that this calculation is done. And it's also important that if somebody comes along and wants to change to a different HRU, value engineering, for instance, I'm not necessarily against that. But if they do that, it's not just enough to say, does your alternative HRU give me the kilowatts I need to meet the requirements here? You need to also know what the delta T is, because if the delta T is different, it may be able to give you the kilowatt demands. But if the delta T is different, then you're going to have to recalculate all your pipe work and your valves and fittings and all the rest of it. So once we've done this and we know what the delta T is, we can then do our network sizing. So we can size the pipe work, a little bit more on that later. You can size the pumps, the thermal store, and the energy source input energy that is into the network. Now, we have a very, it's actually just a spreadsheet. It's very simple, really. And these calculations we do for consultants all throughout the UK on a daily basis, typically. Just to explain very briefly, we put in figures here for the network flow temperature, the differential pressure at the index point on the network, the diversity factor you're going to use, and this is a drop-down box, which then affects the calculations that are in this spreadsheet. Here, this is the thermal store in the plant room. So we've got a duration of peak. Now that defaults to, depending on which diversity factor you use here, the charging time that you want that buffer to go from being completely cold to fully up to temperature, and the fraction of the buffer used. And just to explain that, I would hope, and we'll look at it later, that stratification is achieved within that thermal store. So you will not have a full buffer. It will be stratified, so it won't be 100% up to temperature. So we use a factor, typically 66%, but we can change that. When we come into the long table here, number of apartments of a given type. So this can be as long. We've done calculations where each one is an individual, each line is an individual HRU, or we've done them where we've got 100 of this type and then maybe 40 of another type, and so on. This is the heating load in the apartment. This is your flow. Oh, excuse me. Sorry. Let's go back. This is your flow in space heating flow temperature. This is your space heating return temperature. Your litres per minute of hot water required, temperature of the cold water, temperature of the hot water, calculates out a kilowatt output from the HRU. This is a drop-down box to select the HRU you want, and then everything else is calculated out. So we can see what the primary return temperature will be when the HRU is on heating load. And as you can see, it will always be slightly higher than your space heating return due to the losses over the plate. So this is calculated out here. This is the flow rate that will be needed to give you that energy onto the space heating. Same calculation here for domestic hot water, and you can see how low that return temperature on the primary will be when that unit is in hot water production. So just 20 degrees going back into your network. We have the peak, the average calculations here. If you may have different values in here depending on the different types of HRU. So this is just averaging them out here. Then this is your peak information. So you have your return temperature on the network at peak, 30.1 in this instance, and your flow rate to meet peak demand, 20.25. So you can now start to size your pump and your pipe work, etc. as you go through the system. Coming over here, we've got our volume of the buffer, and in this instance, 100 HRUs, we've got 2,144 litres. And down here we've got the power that you need from the boiler. So you can see here 100 apartments, and yet the boiler power is just 341 kilowatts. Obviously I'm using the term boiler, but it could be any energy source or combination of energy sources, but that will suffice to give you the outputs that you put in there. And as I say, we do that on a regular basis. This electrical power here, which is showing as 0, is just for us if we want to add in the inline element that we saw on one of the earlier slides, where we want to boost that figure, then we can put in a delta T that we want the electrical to input to provide on the primary side, and it'll tell you then what the total additional electrical requirement is of that building if you're going down that route. So once we've done that, we've got a lot of key figures here of what you need for the next stage. So the next thing we need to think about is our keep warm or bypass strategy, or both, which can be done in the HRU in the terms of keep warm, but then also maybe on the network. And we'll look at that a little bit later on, because that is a little bit of a minefield. So we'll have a little look at that. Then we need to think about the layout of the energy centre and the LTHW pipework. How are we going to do that? And we'll look at those a little bit later. What's the consumer expecting from controls within his apartment? How are we going to bill and do the energy? Is there going to be any ongoing monitoring and adjustment? And we'll look at that as well a little bit later on. And do we want something that's relatively new, remote access and control through Modbus, where all the HRUs are interlinked and we can view them from a web browser and recommission them or adjust them as is needed, or have that happen automatically? And as I say, we'll look at that a little bit later. So approach temperatures, why are they important? Right, there's a couple of calculations here done on basically a space heating example. What you can see in this first instance here is we have a 55 degrees C flow into the HRU, and we have a 45-35 on the space heating. But when we talk about approach, it is the flow into the HRU compared to the flow out of the HRU in terms of temperature. And you can see here there is a 10 degree approach temperature difference. So 45 to 55 is 10 degrees. So to give you your 3 kilowatts here, you can see you will get a return on the primary or the network of 36.2, which equates to 137 litres per hour of primary water into that HRU to give you that output. If we now reduce that approach temperature from 10 degrees down to 5 degrees, we can see we've kept the flow in the same, but we've increased the flow temperature going out on the secondary side or onto the space heating to 50. The delta T is the same here. What we can now see is your return temperature on the network has gone up from 36.2 to 42.8, and the flow rate that's required has gone up to 212 litres per hour from 137 litres per hour. Quite a significant increase, and yet the demands are the same. So this is why approach temperature is important. We tend to work on a minimum of 5 degrees. You can go below that, but once you do, you find that this return temperature increases quite dramatically, and the required flow rate increases quite dramatically. So while 5 is the minimum, it's not something that we try to achieve or recommend, because we always try and recommend going as big as you possibly can, because the bigger the approach, the better for your network. So how important is delta T and how do we maximize it? Well, delta T, as I mentioned earlier on, is the fundamental thing that makes heat networks efficient or not efficient. It's as simple as that. It is absolutely crucial on all levels in terms of achieving an efficient network. And I would always state that if there's any decision in the design process that you believe will have a negative effect on the return, i.e. increase the return temperature, then we need to think long and hard about whether that's the right decision to take. Having a small delta T increases obviously flow rates on the primary side, so increasing pump energy use. It will increase the network losses on your network. It'll increase the chances of overheating of the building. It will increase the diameter of the pipes that you actually need to give you that same amount of energy in there. Everything cascades down from that. So as soon as it starts to decrease, it becomes a real issue. So we need to be looking to keep it at the maximum we can at all times. When we start to look at the energy sources, of course, when we then start to look at a requirement for maybe different delta T's, and that's something we need to factor in, but we've got to be really careful that we don't compromise the network based on the energy source. We need to manage the control of delta T around that energy source, which we'll look at later on. But you can imagine if you have a 70-degree network and you're returning at 68, which is not that uncommon, unfortunately, in the UK, if you have a CHP in the plant room, the chances of that CHP are running are very slight. The engine would be unable to really get rid of its heat, and it would probably shut down even if you had an electric demand in the building. Same rules generally apply when you look at other sources. Your condensing boilers will almost, well, they won't condense, it's as simple as that, so you'll lose efficiency over your boilers as well. If you've got solar in there or heat pumps, the chances are if your return, even if they're just part of that network, if your return is 78 degrees, you can 68 degrees, you can see that your solar becomes useless, as does your heat pump. So it's fundamental to getting an efficient network. Just a very quick snapshot from the BESA, the British Engineering Services Association, of course. This is the only currently applicable test or independent test of HRUs. And our 32107, I've used that example of our HRU right the way through. You can see here on the left is a measure of VWAT, which is the volume weighted average return temperature, so the lower the better, and we're sitting right here on that table. We can convert that into annual primary water volumes that are required to give you an output, and you can again see that we're right down at a very low level here in terms of annual water. VWAT's quite a complicated subject. I'm not going to go through it now. If anyone wants to know what it's all about and how it's measured and how we test it, then please drop a little note in the questions or the chat, and we'll address that a little bit later on. So I've already alluded to the fact that we're integrating heat pumps now into lots of networks. In fact, we're doing many networks that are heat pump only in terms of the energy source. So this is a quick snapshot from our heat network design guide, which the first iteration of it was done around about, or I put together about 10 years ago. It's been updated on a fairly regular basis as things have changed and our knowledge has increased. But I'd say about 4 years ago, we went with this particular layout for an energy centre. Now I'm showing heat pumps here, and this is about integrating heat pumps, but actually these energy sources can be anything really in this scenario. But just to explain what's going on here, what we've got is a network flow of 55 degrees C going out here and a network return of 17 degrees, because we've maximised the delta T on the network, which is exactly what we need to do. So we've got a very efficient network here, very low flow rates around that network, all good. And then when you come to the other side of the diagram here, these, as I say, are heat pumps. But what we're actually doing here, we've got to remember we've got a 38 degree delta T, yet the heat pump typically only wants a 5 or 10 degree delta T across it. Now, we don't want to design our network at a 10 degree delta T, because that will give you a very inefficient network here with high losses and so on that network. So we need to manage the requirements of the heat pump to what compared to what we're actually going to see coming back from the network. So what we've got here is our product that we do, which is a Caleffi Legiomix, it's called, and basically all it does is create a microclimate around the heat pump. So What's happening here is the flow water coming out of the heat pump is actually mixed into the return to make sure that the heat pump only ever sees a 10-degree delta T here, and all the other heat pumps are doing the same. We've sized these to give you the output that you need for your network. So it depends on the size, how many you need in this, but you can have as many or as few as you want, depending on the size of the heat pumps you want to go to. How they're controlled is from this thermal store. This is a 2-pipe arrangement. We see many designs where it's done as a 4-pipe arrangement, where you've got flow in and out to the energy source and then flow out and return back in, a 4-pipe arrangement. That, as far as I'm concerned, is a low loss header, and they should be avoided on a heat network because they will harm your delta T significantly. They're also outlawed in most Scandinavian countries, low loss headers, and all you're doing is effectively creating one if you have a traditional 4-pipe arrangement. So the way this works, this pipe work coming into the buffer and this one coming out is bidirectional. So you have your temperature probes on the side of the thermal store. We've hopefully got stratification in here, so you can measure on your BMS via these probes where your stratification layer is. And dependent on what that stratification layer is doing, will dictate what you do with your energy sources here. So let's give a scenario. Let's say we've got a stratification layer sitting roughly here. So we've got hot water at, say, 55 here, and below that stratification layer, we've got 17, 20 degrees sitting somewhere around here. If that stratification layer is moving down, we know that our output from here is greater than our demand on the network here. So what we probably do is nothing for a while, and we monitor what that stratification layer is doing. And if it's continuing to drop, if it's a heat pump project, we probably wouldn't do a lot until the stratification layer is coming down to about here. And once we're right down near the bottom, we know the thermal store is full. We know that we're producing more than we need on this side. We'd start to switch off these heat pumps. If these were different energy sources, we'd possibly start to switch them off in series a little bit earlier on, because we're not too bothered about them running on. But on heat pumps, of course, we want them to keep going all the time, so we probably wouldn't do much till the stratification layer came down here. But you can imagine if that's dropping down and then suddenly it stops, becomes stationary, and then reverses and starts coming up here, what that basically means now is your demand on the network is greater than your output on the in the energy center. So you'd start to bring on your other energy sources, so that they're adding now their energy into the system. The benefit of this 2-pipe system is you don't get the the circulation in that thermal store that harms your delta T coming back to your sources. But the other thing is, in this configuration, your thermal store can augment the output of your energy sources here. And the reason that's important is we're talking about peak demand a lot of the time when we're sizing networks. Now, if I pull some figures out the air and say we've got 500 kilowatt network, that's how much we want. We don't have to have 500 kilowatts here. We can, and again, I'm just pulling figures out to give you an idea here. I'm not doing a calculation, but we may only need 450 kilowatts here, even though we need 500, because at peak, when you need your 500, the thermal store, the output from the thermal store coming up here and joining the output from the sources, that this store augments the output of the sources, and therefore you've got your 500 kilowatts that you need, because your sources of 450 coupled with the 50 from the thermal store give you what you want. So the thing to remember, it's bidirectional. It will either flow in and fill your thermal store at times of low demand, or use the thermal store at times of high demand on your network. Best to keep this as a minimum a ratio of 3:1 height to width, because we want to see that stratification layer. We want to be able to see it very easily on the BMS, and we want to be able to control purely from that stratification layer. So, as I mentioned, that's been in our design guide for over 4 years. It was nice to see that in CIBSE's Heat Network Design Guide that came out about 3 weeks ago, I think, they've actually copied this side of it almost identically, in that you can see here 3 heat sources that happen to do 2. This is your bidirectional pipework again. Your thermal store is again in sitting there in with a 2-pipe arrangement and can augment the output and so on. So we've already gone through what we talked about here. You can see in the CIBSE design guide, there's 3 other things we maybe just need to talk about here. Now, I don't want to get too bogged down on this because these are very specific to specific projects, in that in the majority you probably wouldn't have any of these, or you might have one. It depends on the project. Whether these go in is determined purely by the project. So this first one here might be, you might have a building where this might be an existing building where the return temperature is relatively high, but you can connect another building onto it that is a new build that has a nice low return. So you can use that return temperature coming down here because it's high enough that you can use that in your new building to bring a return back from that building that's much lower, and obviously then lower the return at point B here. So, but it depends. You may not have a building where you have that facility to do that. So that's what I mean when I say these things here are very project specific. Here they've introduced another heat source. It could be a heat pump and so on. They've introduced it in the same way. The idea here was to have this as a constantly running energy source to meet your base load, and probably something like a heat pump, because it's going to see the lowest return water possible on that network coming in here. And again, would you always do that? No. Are there some projects where it'd be a good idea? Yes, absolutely. And we can see there's potential here to put in another heat source here, again getting this return. Obviously, the idea here would be, if this is going to be a heat pump down here, this probably wouldn't be located in this position. And actually, there's later reference in CIBSE's design guide to that being a condensing boiler, because you can get it to condense really well because of the low return water that's coming back here. And these items, energy sources, could be your base load items, and then these ones on the left hand side are just brought in every now and again when you need to get peak or to charge your buffer vessel here. So it was quite good to see that in that design guide. In terms of the thermal store, again, this is pulled straight from the design guide, CIBSE design guide. What we're trying to do, if I just focus on this bottom graph here, is have instances in the typical day. So this is this is looking basically at one day. You've got low demand here through the small hours of the morning, starts to ramp up as people are getting up. These areas here are covered from the energy purely from the thermal store that's on the network. At this point here, we're now using the lead heat source to, this could be your heat pumps if you have a nice mixed amount of energy source or types of energy source. And then here we have, sort of auxiliary sources kicking in to hit your peak demand. Still using the thermal store here to augment it. And then as the peak starts to decline, you've probably used up, hopefully, if it's everything sized correctly, your thermal store here. So there's no thermal store left to use, but the peak's now passed and it's dropping down. And at this point here, where the orange kicks in, that's where your lead source is now adding energy into the thermal store. So you're reloading that thermal store ready for the next peak, and so on it goes. I think it's quite a nice little graph to show how that thermal store should be in operation in a good system. So I'm going to have a quick look at the latest release on CP1. Because there's a couple of aspects that we need to take into account, and one of the things I mentioned earlier on was this varying of primary flow temperatures or future proofing of a heat network. I mean, I would suggest that they're interchangeable, varying primary flow temperatures and future proofing. What CIBSE's CP1 is saying is that the flow temperature these are the sections where it's mentioned, and this is a direct quote saying that it maybe look to change it in summer. So to have maybe a lower temperature in summer because you don't need it. And then a little bit later on, it says maybe you might want to do that seasonally. So whereas in 1.3.4, it was talking about effectively 2 different temperatures, summer and winter. Here we're talking about seasonally, so maybe 4 differences or 4 changes in temperature. But then in 2.4.3, it talks about weather compensating that primary system. So if we're going to do that, and that's a really good idea, what does that mean for the equipment in the apartment and the HRU? So what I've done here is do a calculation again using our simple spreadsheet, and you can see I've used a 70-degree primary flow temperature here, and we've put all these values in, and we've selected the HRU, so everything's good, no errors, no alarms, all the figures in there ready to go. If we now, what we've got here actually is a radiator system running at 65-45. If you now lower that primary flow temperature down to 65, you've now got 0 approach temperature. You've got 65 in and 65 out, and the network will at that point fail, because what will happen is all the HRUs on the network that are on heating demand will suddenly open all their control valves 100% to try and achieve a flow temperature that is unachievable, and the system will actually crash and the network will fall over, and that will manifest itself as a failure in hot water. That would be the first thing that will be noticed, probably by the tenants on the extremities of the building, but it will crash. So you can see in this scenario, unless we're actually altering the output or the set points on the HRU, the amount we can vary the primary flow temperature is very, very small, literally 4 degrees in this scenario, which is a very, very typical scenario of a UK network that we tend to be doing at the moment. 70-degree flow is quite common on heat networks, with the exception of the heat pumps now that we're starting to see, but that's very common, and this is a very common radiator set point. Well, here there is no real area for fluctuating or modulating the primary flow temperature. If we do 2 more calculations here, what we can see, I've now moved that down to 65. I've moved the flow temperature from the HRU down to 60, and we can see everything rebalances itself and it's fine. But the critical thing here is the HRU has to have its space heating temperature adjusted down to 60. In this calculation here, we can see I've dropped it further, now down to 60. So from the original calculation, we've dropped 10 degrees from the primary flow temperature. And again, we've dropped the HRU output down another 5 degrees to 55. So we've kept our 5-degree approach, and we can see again that everything here is absolutely fine and the system is working. But my comment here is really that we know where HRUs are generally installed. It's inside the tenant's apartment behind a locked door, which is very difficult to access. So if we're going to vary our primary flow temperatures and we need to be able to change the settings on the HRU, then we have to have some remote way of doing that, because to seasonally adjust the HRUs, or worse still, to weather compensate the primary temperature, we'd have to have access into each apartment every single time that we wanted to change that primary flow temperature. And that is just simply impossible in today's world. So what do we need to do? Well, we need to remotely connect to the HRU and control them. And we see that in CP1 2.6.10 says consideration should be given to whether the HRUs and substations will have communication systems to allow remote interrogation of performance and remote setting of controls. And then best practice 3.3 says allow remote access into the HRU settings so the changes can be made, fault addressed and performance checked without needing to visit the HRU. As it stands today, there is only one way of doing that, and that's with a Modbus system, which is a standard feature in our HRUs. And once you connect that up, you can remotely, through a Windows browser, connect to all the HRUs in a building, and you can adjust settings globally of all the HRUs or adjust HRUs individually. So it gives you that flexibility to do it. We also have the ability within our software to set up automatic changes. So we can take the flow temperature, for instance, into the meter, the energy meter that's in the HRU. That records what the flow temperature is on the primary side. We can read that data, and when we can then get the HRU to follow it so that it actually keeps an approach temperature, and the HRU will track a stable approach then. So as the primary temperature fluctuates because you're seasonally adjusting it or you're weather compensating it, the HRU automatically adjusts its own settings and just follows it to keep your 5-degree approach if that's what you've originally set. There's another quite concerning fact which has come from a company called Guru, who you may be aware of. Again, if you want more details of what they do and so on, then leave a little note in the chat. Guru have a software that monitors heat networks. They monitor various different networks. They're not tied into Alltechnic at all. We do partner with them on certain projects. But their data, their software data shows, and this is pretty much every project that they monitor. It shows that the losses that network had on handover typically double within 3 years of handover, which is a really telling fact, really. And how does it do that? Well, it's people making little changes over a period of time, maybe not understanding what effect that's going to have on the whole network. So you can imagine you really want to have constant commissioning here on a heat network, so you can regularly keep an eye on what's going on and adjust what you need to on the HRU as things change on that network. If you can't see it, you can't manage it. It's as simple as that, really. I'm not going to go into too much detail, but there are major benefits in having remote HRU connection for the consultant, the installer, the ESCO, the client. There's fault reading before the tenant even becomes aware that there's a fault on the HRU. There's the remote commissioning. You can even change temperatures of the not only the set points, but also things like you can set up alarms so that you can see when maybe hot water's not been used in an apartment for a week, and you might want to just do a courtesy check to see that the tenant's okay. Or you can see things, that the temperature in the room is constantly set at 10 degrees and it's never been changed, and you can adjust that remotely if you wanted to. There's so many different things. I'm not going to go through that here. I don't think it's the forum for that. And this is just showing you some of the software remotely where you can go on and change the temperature set points and various other things like flow temperature, return temperature compensation or limitation we have in our HRU, and a number of other things that can all be done remotely. What does that mean? Well, this is taken from the Guru software, and what you can see here, this was the reading that was coming from the HRU. It was spotted that the delta T wasn't very good. There was a reason for that when they interrogated the HRU, and they adjusted the HRU remotely, and lo and behold, the return temperature dropped from that HRU. There was no access at site here. This was all done remotely. The adjustment to the HRU was done remotely, and you can see the delta T from that HRU more than doubled just with a simple keystroke. This is what the front end looks like. Again, I'm not going to go into detail here. It's not the forum for it, but you can see we've got some very nice, simple sort of red light, green light, amber light warning dials that people can instantly see what's happening on that network. It might be, changes in flow temperature, the return temperatures going up, what's going on, all those kind of things. And then you can look into it in greater detail here. Anyway, I'll move on from there. So just coming on to one of the guidance notes that was released fairly recently. I was involved in it with Gareth Jones of Furheat and also Arup, who put this little guidance note together. And it was a reaction to comments from the market about the 50 degrees C domestic hot water temperature. That was in the original CP1 that was released, I think it was 2015 originally. It's also echoed again, of course, in the update, and it's become the standard. It's now accepted by the HSE that from an instantaneous HRU, it's low risk from a Legionella point of view. So we're happy with a 50 degrees C temperature. There was some feedback from the market, I believe, from both consultants and contractors that raised concerns. One of them was to do with the TMV regulations and achieving shut-off should you have a failure of the cold water supply, part of the TMV regs, of course, and also the fact that you're now providing hot water from the HRU at 50 degrees C means that you don't have your 10-degree delta between the hot water into the TMV and the mixed temperature out. So they were the two concerns, basically. So we worked with Furheat and Arup on that to have a look at it, because we were Altecnic happened to be the biggest supplier of TMVs in the UK. So we looked into it. We put this proposal together, and we've got two little schematics here, one with a manifold system, which I'll mention a little bit more about a little bit later, and then a more traditional system, if I say that, on the right hand side. And what you've got to remember is the HRU, of course, is taking cold water that comes into the apartment and using heat exchange to create your domestic hot water. So if there is a failure in the cold water supply, so long as there is no isolation valve from this junction point here to the TMV, and that includes fitted to the TMV, so long as there's no isolation valve on that part of the circuit, the moment cold water fails because someone's turned the IV off or there's a failure on this side, your hot water out will also fail at exactly the same time. It is impossible to isolate it after that junction, so your hot water can only ever fail if the cold water fails. So you've achieved your TMV reg shut off on the event of cold water failure, but we've done it from the installation rather than expecting the TMV to do it, because it now hasn't got that 10-degree delta that we talked about. And so that covers the shut off. Then the other comment, of course, is, well, we're going to have much lower than a 10-degree delta T between mixed out and hot in. So is the TMV going to be able to give you a stable domestic hot water temperature? So we sent some TMVs off to Enertech. They're a UCAS accredited test house, and got them to test exactly that. So we set the flow into the TMV at 50 degrees, set the TMV at I think it was about 45 degrees. In fact, it was slightly higher than that, I think. And you can see that it was incredibly stable. There was no fluctuation in that at all. And that was stable enough to pass the TMV regs comfortably. So we've covered both the objections that came back from the 50 degrees C hot water set point from the HRU. So that guidance note is out now, and these schematics are in there, and it can be achieved. So moving swiftly on, we're talking now. Sorry, let me just go back. Just coming onto this approach here, where we're using a manifold system for the hot water out. What we're looking at here is using microbore pipework out to individual outlets. And the reason for that is what we're trying to do is reduce the response time for hot water to be produced at the tap, so that we minimize that time that the tenant has to wait for the hot water to come out of the hot tap, basically. So by reducing the volume of water that we've got in this part of the network or within the apartments, the domestic pipe work, then we're trying to speed that up. Now, in the BESA tests that I very quickly referenced earlier on, there is a response time test, and to pass it, all HRUs need to produce domestic hot water at the required temperature within 15 seconds. And all the HRUs that have published data have shown that they can do that. Now, 15 seconds is a relatively quick time. I think I'm right in saying that the NHBC state a minute for hot water to be produced, so that's a lot longer than the 15 seconds. But we need to remember, for the BESA testing, the temperature probe was sitting just outside the HRU. So you've got your 15 seconds for the HRU to react, then you've got to purge the water that is in here. So if we can reduce that as much as possible, that will speed up the response time. But we also need to think about the primary side, or the feed into the HRU, and where the hot water is coming into the HRU. We'll come on to that as we go along. So what do we have to do? Well, these are pulled straight from CP1 again. What we're saying is this layout, which is actually more traditional for the UK, where you've got a single riser and then long laterals, is not preferred. And it's not preferred because if you have a system like that, you really end up driving yourself down into a cul-de-sac where your only way of achieving hot water in a reasonable response time is to keep circulation constantly flowing down this lateral pipework. And when you do that, you massively increase the losses that you will get in the building. You increase the chance of overheating in the corridor. And you then have to have your preheat switched on in all these HRUs, and you may even have to think about having a circulation at the end of each lateral run just to make sure that that water stays hot. Because if that lateral goes cold, and of course it's compounded if that pipework is oversized, which is unfortunately generally what we tend to see, an oversizing of pipework in the UK, then that compounds the problem even more. And then you have to get lots of circulation all around the building, and we find then that's when your delta T is lost, your building overheats, as I say, and all those things that we talked about earlier on all cascade down. So the recommendation in CP1 is to go with multiple risers wherever possible. So shorten those laterals. You can then have bypassing just here at the top of each riser, and you can have HRUs without any bypassing in them whatsoever. So the keep warm can all be switched off, and you've reduced your losses, you've reduced your response time, and you've reduced the inertia in the building of the whole network. And adding to that, you can see this is the worst case scenario at the top here, where you've got multiple risers. Single riser coming up here, spreading pipework down the corridor to HRUs that are installed well into the each apartment. That's the worst case really that you can come across. Getting slightly better is to mount the HRU on the inside wall here, so you've minimized any pipework inside the apartment, but again you've still got single riser, lots of lateral pipework here, lots of chances of this overheating and so on. And then the best case scenario is down here where we've got the multiple risers, so 2 in this scenario. HRU is really close. We've minimized all that pipe work, we've minimized our reliance on preheat, and then we can get a much more efficient, low inertia, fast reaction system if we install it that way, which is all tied in with keep warm in the HRU. What I just want to touch on this is it is a minefield. Unfortunately, there are a lot of HRU manufacturers that have used the term trickle bypass, and I really hate that as an engineer, because what is a trickle? One man's trickle is a fireman's hose to another guy. What is it defined as? It's unknown, and there is a HRU on the market in the UK, unfortunately, that has a flow rate of 100 litres per hour, and it's marketed as a trickle bypass or a trickle keep warm. 100 litres per hour is not a trickle, and you can imagine if every HRU is passing 100 litres per hour, you've effectively got a constant volume system. There's very little pump modulation in the plant room. It's a nightmare. So we should avoid using the term first and foremost, but actually, do we really need keep warm? It's, in my view, is needed because of slow acting HRU control valves, long and oversized lateral pipework, and long and oversized domestic hot water pipework. If you have those 3 things, then you have to have a high flow rate going through the HRU, and you consign your building to high losses and all those negatives that I mentioned before. What are the downsides of keep warm? Increased energy use on the network, decreased network delta T, increased losses, higher bills to the tenants. Can you achieve the 15% losses that is mentioned in CIBSE CP1 on your network? I'd argue that you can't if you have all the keep warms running. And this last point is really quite a fundamental one, really, moving away from the negative effects on efficiency. You know, should we be relying on something that the tenant owns, that's in his apartment behind a locked door, to make the system work? And the clear feeling for me is that that's not a good idea at all. What happens if a tenant, not happy with the fact that he gets a bill when he goes away and he's not using his HRU, turns the isolation valves off on his HRU so he doesn't get a bill? You start to lose your keep warm, you start to lose your pump turn down, minimum flow rate for your pump, etc., etc. And the tenants are very social, and they'll talk to other people, and as soon as you know it, they'll be at summer, everyone will be going away and turning their HRU off. What does it do if you turn HRU keep warm off? Well, you can see the improvement here. This is the VWART acronym that I used earlier on. Your volume weighted average return temperature. These are the tests that are in BESA, low temperature and high temperature. This is for our unit, which is 28 and 27. If you turn the keep warm off on the HRU, it drops to 15. There's a massive improvement. There's a consequential reduction in annual volume of flow rate that you need to flow around the building as well. So if we can possibly switch it off, it should be something that we look to do. Thank you very much. I hope that wasn't a lot to fire at you. As I say, if there's any questions been added, I'm more than happy to go through them now. And yeah, please feel free to shout up any questions you want.
No, thank you, Neil. Very good. I'm sorry, you probably could have talked for another hour on that, I think, if we'd let you, but it's great to see how knowledgeable you are on it, and I think some excellent stuff on there that we'll probably all take away for when we're looking at these district heating networks as well. Yeah, so just I suppose just to thank Neil again for doing the presentation, everyone for attending, and just if anyone does have any questions, please use the chat function to ask, and I'm sure Neil will answer them as best as he can. I know Robert's tried to field a few questions for you has been going through, but I think there was just one question from me, I think, just at the start there, Neil, just about if we're trying to reduce the district heating flow temperatures as much as possible, should we be looking to produce domestic hot water by local point of use semi-storage electric water heaters?
Yeah, it's quite a long subject, that really. It depends on the network. I mean, I guess people have heard of 4G, 5G networks and ambient loops, and if you get down to flow temperatures for ambient loops, then really at that point a HRU really doesn't become the right piece of equipment to install on an ambient loop. You can't get the hot water you require. So at that point then you've got to look at an alternative way of producing domestic hot water. I do personally feel that while ambient loops undoubtedly are a really good idea and a great way of saving energy and carbon, they are difficult in many scenarios because you need consumers and prosumers, so people who have cooling, people who have heating, and you have to get the right balance to make them work. So it can be very problematic in getting the right mix of buildings on the ambient loop to do that. If you come back from the sort of ambient loop networks to networks that are running at 50-55 degrees, then you can achieve that with a HRU. There's hopefully I showed that on one of the slides earlier on, and having that, if you need it, that little extra electrical boost on the primary side that is controlled by the HRU, and that's quite critical, because then if it's controlled by the HRU, you can turn it on only when you're producing domestic hot water, and that is really the key here, because then you only have to apply the diversity that's applicable in typically DS439, so you have a really high diversity factor. When you start to do that in a cylinder, then your diversity is much less. So your additional load, electrical load, then is correspondingly significant in that building because of the overlap of people, of the cylinder reheating and so on, really. I think not answering a question that hasn't been asked, but just something that might trigger people to have to raise a question, is one of the things that I often get asked to do is to look at networks that aren't maybe performing very well, and the energy meter that is typically installed in a HRU is a great way of diagnosing what's going on in the network. You can very often just simply go into an apartment, have a look at that heat meter, look at the data, because it's telling you lots of things. It's not just telling you what the energy is used, it's telling you flow temperatures, return temperatures, flow rates going through, when it's in standby, when it's in heating mode, when it's in domestic hot water mode, and you can diagnose an awful lot from that energy meter. So it's a good place to start if anyone ever has to go to a network and see why things aren't performing as they should.
Yeah, no, I think it's an important thing to take away, is that obviously every project's different, and obviously there's a number of different ways to skin a cat. So some will be correct for that installation that you're looking at. So, but I suppose that's our challenge as engineers, is to come up with the right solution for the right scheme. So.
Yeah, it is something that is close to my heart. That I've said for a long time, every heat network is different, and every heat network needs the right solution for it. And to try and have a piece of equipment that is all things to all men, or all things to all heat networks, is almost impossible. And one of the things I did when I designed the latest HRU that we do is all the features and functions that we put into it, we made sure they were configurable. So everything in it can be switched on, switched off, timed, configured. Every single aspect of that has that flexibility in there. And the idea being that once we know what we're trying to achieve on the HRU, on the network, once we know what the energy sources are, the HRU can be configured to match that network. It's no good using one size fits all, because we know one size fits no one at the end of the day. We now have the ability to configure the same HRU, but configure it in a completely different way, dependent on a system that has long laterals, and then a system that's got short laterals, and a system that has different tenant occupancy types, and so on. It can be configured, and that's really key. We've got to be flexible if we're going to get the maximum savings we possibly can.
Neil, I don't think we've got any more questions. Sorry, we've just got one just drop in actually now. Maybe that last question, and then we can wrap up.
Yep. Well, sorry, what's the question?
I think if you click the chat function, Neil, should be able to. It might just be easier for you to read it than me reading it.
What would you suggest then if folks go on holiday with the HRUs and the pumping of unwanted heat and costs to them? Would it be best to have a pump selection of a jockey pump between design, say 25% for less? Yes, okay. A few things to mention there. I'm a big fan of jockey pumps, absolutely. Just one little thing to note as well is that the current, standard, if you like, if I word it that way, of for pumps is that they can go down to flow rates that are really low and way down on what people have traditionally thought was, a set figure. And I say that because mentioned in that then is 25%. And I was on the steering group of one of the heat network design guides that was going to be released, and we had somebody from Grundfos on there. And we were talking about this reduction, and the majority of people in the room felt that a typical variable speed pump from peak would drop maybe to 25% at idle. It was a common figure that was mentioned, and I thought it was less than that, I'll be honest. And we ended up sort of getting the Grundfos guy in the corner and poking him until he actually put a figure on it. And the figure he came up with is, he said it was nearer 5%, not 25%. So that's quite, I think, a good thing, an important thing to remember, really, that today's pumps can get down to really low idle flow rates without any issue. So it's kind of a double answer, really, for that question. If that pump is sized correctly, then you can almost certainly get the range or the width of performance that you need down to a really low idle level and peak. If the pump is oversized, of course, then your idle level may be way too much for the building. And so I'm quite a fan of jockey pumps, but I think nowadays you can probably get away with not using them. The other sort of, maybe it's a question in that question that I'd like to just mention is that one of the things that we have seen on networks is tenants playing with the HRU, adjusting things and so on. So it's really important that like flushing bypasses are integral to the HRU, or it's part of the fittings that go onto the HRU, where it's like a lock shield valve, or the way of adjusting it is hidden, so they can't make any adjustments, because you only need one or two flushing bypasses opened up, with all good intentions, and your network delta T is gone, and you lose your variation in your peak to idle speed on the network as well. But for me, the concern is that tenants will isolate the HRU, and it is for that reason that I'm a very pro bypassing on the network and not using the HRU preheat. You know, you can do a valve arrangement at the top of the riser, which you know, it can be commissioned properly, can control the flow through that bypass to the right amount that allows your plant room pump to drop right down to its minimum flow rate, and still allows enough flow through to keep the network warm, ready to produce domestic hot water. And then you're not relying on the tenant and what he's doing in his apartment. Your pump is always protected. It can't be compromised by having a flow rate that's lower than what it needs, and you take that away from the tenant. I've had a few comments on that saying, well, how does it work with, you know, the bills the tenant's going to pay? Does that mean they wouldn't pay? And do they pay more if it goes through the HRU and all the rest of it? And it's a non-question, to be honest, because last time I looked, ESCOs are not charities. So they're all there to make money. They're a business after all, and they want to make money. So it doesn't matter whether the bypass goes through the resident's meter and therefore is registered on that meter to the tenant, or it goes around the bypass. Regardless of where that flow goes and that energy goes, the tenant will pay for it. He'll either pay for it in his unit charge, or he'll pay for it in his standing charge, depending on where it goes. So it's a non-objection to say, well, we've got to think about who pays for it and where it's paid and all the rest of it. The tenant will pay for that anyway. So it makes much more sense to do it on the network, protect the network from changes made by the tenants, and you know, then everything can be commissioned, everything is fine, and you can walk away from that building knowing there'll be far less chance of the losses increasing over time, because you're not allowing people the facility to change things and make it worse. Sorry, that was a long answer. That question on the BMS to check and modify the flows of the HRUs remotely rather than talking about recommissioning, can we get Modbus to do that? Yes, absolutely, you can. Absolutely, and we have supplied our Modbus telegrams to BMS companies so that they can do that. You can do it through the BMS. You can do it through a separate Modbus system. I prefer that rather than the BMS, but you can do it either way. It's no problem. It's got to be the way forward here. It just allows you to adjust, or I'd use the word constantly commission the system. I think that's really how we need to think about that. But yeah, the BMS can do it. And if the BMS is also controlling your flow temperature out of the plant room, then you can absolutely have it controlling the HRU to keep that approach temperature that I talked about, so that it adjusts the HRU settings when it adjusts the flow temperature going out. So it's a very good way of doing it. My only negative comment would be, I personally prefer to monitor it from the meter in the HRU, purely because you're going to get some losses around that network. So the temperature that the BMS is putting out in the plant room will be slightly different to the temperature that's actually going into the HRU. So you can take away a bit of that discrepancy. And also, of course, you take away that lag of, well, it now may be 60 that's coming out the plant room, but how long does it take for that 60 to get out to the HRU because of circulation and so on? So I prefer to do it from the HRU, but the BMS is absolutely a great way of doing it. Yes. Sorry. Yeah.
Neil, I was going to say, someone's asked if they could get a copy of the presentation. I know you've sent it to me previously. Is that okay to share that?
Yeah, I'm happy for that to be shared out. Yeah, no problem.
Lovely. Excellent.
And you know, my details are on the last page as well. So if anyone, you know, drops out the call and then thinks, damn, I should have asked such and such, or, you know, in the working week they come across a network, or they've got a question that arises on a project, then absolutely feel free to contact me. It's basically what I do for Alltechnic. You know, it's that technical side of advice, if you like, or with building services consultants. So feel free to contact me and ask anything you need, really.
No, excellent. No, well, thank you very much again, Neil, and I'm sure everyone's found that quite knowledgeable. But yeah, no, I think we're all done with the questions. Or like I say, if anyone's got any questions, they've got your contact details to reach out to you direct. So excellent. No, thank you very much, Neil.
That's all right, no problem. I think we've just got somebody who's actually typing now, though, or it says on my computer. So it might be a question about to arrive. Yeah. Ah, okay. Yeah.
Yep.
Thank you, Garfield. I will, as I mentioned, Philip. I do this just well, you could probably tell off the cuff. I don't have notes. I just do it as it comes in my head, really. But I will at some point add some notes to the slides, and I'll send them over to you, Philip, once I've done that, so that you know, people who want to actually have a read through the notes can do so.
Yeah, that'd be greatly appreciated.
No problem.
Lovely. Well, thank you very much.
That's all right. No trouble at all. Thank you, everyone who joined, and I hope you found it useful.
Yeah. Have a great evening.
Thanks. Cheers, all.
Thank you. Cheers.
Bye now.
Bye.
Bye.